The University of Huddersfield, inspiring tomorrow's professionals.
Well, good morning, everyone. What a nice way to start the morning listening to that jazz. Okay, so yeah, I'm in the second year of my PhD project at City University of London. And I'm between departments, between the computer science department in the music informatics research group, and between the music department working with Armstrong, who's a electronic music composer. Those of us who are supercollider users might have heard of him. Yeah, my research is all about the perception and generation of expressive timing in rhythm. So what I'm going to talk about, after a quick introduction, I will do it really quickly because a lot of you will know what I'm talking about. I'll talk into some detail about some of the models that I'm using. So there's GFNN, which is short for Gradient Frequency Neural Network, and LSTM, which stands for Long and Short-Term Memory Network. So I'll talk about them in some detail. And then I'll introduce the GFNN LSTM, which is one of our contributions, which is a hybrid network of the two. I'll then talk about an expressive rhythm experiment we've done with the system, share some results, and talk about some of the future work we're doing. So, just to start, I'd like to start with this quote from Curtis Rhodes. Composition is not a matter of filling or dividing time, but rather of generating time. So this is what I mean in the title of the talk, generating time. We often, when we think about generative systems, especially in terms of music, we often think about things like generating harmonies, generating pitch. But we see time as one of the generative outputs of our system. And when we think about time in music, we consider two fundamental principles of time in music, and that's the pulse and the meter of the music. We all know what the pulse of music is. Here's an example. This is a cockatoo, not a parrot, called Snowball, who can dance. So yeah, so we all know what pulse is. It's an isochronous, more or less, beat implied by the rhythmic events in the music. But actually, pulse is one layer of a multi-layer system, a multi-layer hierarchy which divides time in different ways. So we can divide the pulse or extend the pulse to create these hierarchies of strong and weak beats, and this is called the metrical structure. But in performance, in practice, you know, it's not that simple, it's not that straightforward. As a performer, we introduce our own expression into our performance of music. And that expression can be multifaceted, so timbral, playing with velocities, but also rhythmic expression. So here's an example of that. Find my mouse. So when we play with rhythmic timing, we play with the expectation of when an event should happen. So we get these undulating patterns. So with the rhythm and the meter, our perception of the meter, the expressive timing is playing with the degree to which the meter is being expressed. And this forms a new sense of time. As the meter is being changed, a new sense of time is constantly being developed into the state of flux. So yeah, our research concerns this interplay. So we have rhythmic and meter perception, an expectational prediction, and then a new rhythmic production, which feeds back into our perception. So this is a little loop, cyclical loop. So the models that we'll be using, that we use in my research, are two main ones. So we have the first one called the gradient frequency neural network. Here we see an experiment which shows the phenomena of entrainment happening. So here we have a bunch of metronomes, and they're all connected via this plate, which is on these rollers, and they're set off at different phases from each other. And as the pendulum on the metronome swings in one direction, it exerts a force onto the plate. And over time, this force affects the other oscillations in the system until they all become synchronized. And now they're basically synchronized. And once they're synchronized, they'll remain in that state until something comes along and changes it. So this is called entrainment, and it was first discovered in 1657, so it's well documented, and it happens in physics, chemistry, biology, and it's a fundamental musical trait as well. So Ed Large takes the idea of entrainment into neuroscience with his model of nonlinear resonance. So nonlinear resonance is a model of the way our nervous system resonates to pitch and rhythmical frequencies. So it can explain perceptions of our pitch and timbre, feelings of stability and dissonance within music, and also pulsometer perception, and all these arise as patterns of nervous system activity. So here we have a diagram of a very simple neural oscillator. You have two neurons connected in one's excitatory, one's inhibitory, and this makes a neural oscillation. And Large introduced this model, which is a type of oscillation called a Hopf oscillator, but it's had some higher order terms expanded. Don't panic if you're not that familiar with the maths. I'll take you through it quickly. This part means it's a differential equation, so it's describing how the oscillation changes over time. The main variable is this Z variable, and Z is a complex number, so it has an imaginary part and a real part. And when we talk about oscillation, that's a very elegant way of describing an oscillation, because you can treat the phase of the oscillation as the angle of your imaginary number in the complex space, and the amplitude of the oscillation is the magnitude of the complex number. We have a bunch of parameters as well which change the behavior of the oscillator, but I'll just take this one, the omega, which is the natural frequency of the oscillator, and that's usually in radians. I say natural frequency because this oscillator entrains, so the observed frequency differs from the natural frequency. We also have here a connection to an external stimulus, that xt is the external stimulus, and that's called a passive connection. You also have an active connection, which is a connection within the oscillator itself. And then finally, and optionally, you have this connectivity matrix, which can connect oscillators between to each other by that C matrix. So when you connect several of these oscillators together, and you distribute their natural frequencies along a frequency gradient, which is where the name gradient frequency neural network comes from, you get this sort of behavior occurring. So here we have a frequency spectrum. The dashed line here shows what you might get from a linear filter, such as a cone filter. So you have two fundamental frequencies, stimulus frequencies here, F1 and F2, and you see the small peaks around F1 and F2. The normal form of the oscillator is the lighter line, which is the same differential equation but without the higher order terms. And that you get stronger resonance on the frequency peaks. But then the canonical model, which is the fully expanded model, shows all these extra resonances occurring. And they are called higher order resonances or nonlinear resonances. And they happen at really interesting frequency relationships to the stimulus frequency. And these frequencies can change over time. So here you can see a kind of spectrogram, and you can see around 24 seconds there's some change happening in the structure of the signal. So that might be a tempo change or some kind of meter change. So I mentioned about the connectivity matrix, C. That these matrices can actually be learned through an online Hebbian learning process. And here's the equation that describes that. I'll take you through it quickly. Again, it's a differential equation. And C is, again, another complex number. So it has real and imaginary parts, magnitude and phase parts. And you may get some connectivity matrix which looks something like this. So what you see here is strong connectivity to an oscillator's local area, and then connections appearing at interesting harmonic relationships to that frequency. And here are some papers that have explored GFNNs when applied to rhythm. So we have things like pulse detection, syncopated rhythms, setting rhythms into categories, analysis of polyrhythms, and also some of my earlier work on melody and rhythm prediction in symbolic data. So the second model I'd like to introduce is the long short-term memory network, which is a recurrent neural network. And the classic RNNs can theoretically learn patterns at any length, theoretically. But in practice, this is difficult to achieve, to train a network to rely on some important inputs at a long time delay. So these long-term dependencies are often lost, and it leads to good local structures, but no long-term coherence within the network, and this is called the vanishing gradient problem. So LSTMs were introduced to overcome this problem with the vanishing gradient, and it does it by introducing some additional gates. So we have here A is the input and B is the output. We have here the central node, which is a sigmoid or tanh activation function. But then we have this self-connection here, which is called the constant error carousel, or the CEC. And as the name suggests, this ensures that you have a constant error flow back through time. That can be reset at some point by the forget gate here, F. And also, there's a couple of gates which control how information flows in and out of the CEC, the in gate and the out gate here. So all of these extra connections on the classic RNN have a weight associated with them. So there's a lot more parameters to train with an LSTM, which can mean that training is slower, but you get a much better performance. So here's some examples of an RNN training a prediction on a time series versus an LSTM. And you can see that the recurrent networks often result in some kind of chaotic oscillation, perhaps, or just a mean of the time series, whereas the LSTM can follow it a lot more closely. And LSTMs have been used for music for quite a while. So Ekin Schmidhuber's the person who introduced the LSTM in the first place. Used it for some blues chord improvisations. They have also been used for beat tracking models and some other computer-aided music composition. And again, in my previous work, I've been using it on symbolic data. So one of the things that we've been contributing is a combination of the GFNN and the LSTM. So we have the GFNN, which serves as a perception layer. So the input goes in, and we get some resonance occurring which serves as a perception of the meter within the piece. That then gets passed through this different connections into the LSTM layer, which serves as our prediction layer. So we train the LSTM to predict the next point in the time series. The work I'd like to talk to you a bit about today is our work with expressive timing and rhythm models. So we've been looking at the Mazurka data set, which is a data set of Chopin piano compositions. So yeah, we conducted several experiments with GFN LSTMs using audio data, which is different from our previous work. They have expressive variations, but they're all in 3/4 time, so they all have some metric similarities. And also we've been experimenting with the oscillator parameters and Hebbian learning within the GFN layer. And here's an overview of our system. We have audio input. It's taken into a mid-level representation, which is an onset detector called complex spectral difference. That's then sampled at around 86 Hertz. So each sample is about 11 milliseconds of data. And the network is trained to predict the onset detection function. So we have 50 sequences from the Mazurka data set, 40-second excerpts, so that's around 172,000 data points. The GFN had 192 oscillators on a rhythmic frequency range. 2 oscillator models, critical and detune. The detune one has more entrainment within it. The critical one has a sort of damped oscillator effect. And then 3 Hebbian learning modes, so no learning at all, critical learning, which is online learning, and then critical learning with an initial generic state. And the LSTM blocks were all fixed at 10, and we used R-prop minus and 5/4 cross-validation for the training. It was a 2-step process with the GFN in MATLAB and the LSTM in Python with PyBrain. And just quickly about the different learning methods. This is a connectivity matrix you might see from online learning. So you get peaks in the connectivity matrix at tempo-relevant points. This is the generic connection, so you see that there's no, it's not specific to 1 meter or tempo. And then after you've done online learning with that initial state, you get something that looks like this. So you have some generic connections still, and a general stronger resonance overall. And here are some of our results, which I'll present at SMC this year. And you can see that the best performance is for the detune oscillator with the initial condition for the online learning. And we were getting an F measure prediction of around 71.4. Compare that with the beat tracker performance on this data set, which state-of-the-art is around 72 F measure. So we're approaching state-of-the-art with expressive rhythm onset prediction, not beat tracking, which is arguably harder. So the future work is we're going to be working on a Python implementation of GFN. Actually, that's now done. So that will be released as an open source project in tandem with Ed Large's MATLAB toolbox, which will hopefully be released soon, and will be found on GitHub. And we're working on a beat tracker, which is going to be submitted to the Merit. So following the same pattern, but instead of predicting rhythm onsets, we're just predicting pulse onsets. Because of the good results we got on our expressive rhythm timing, we reckon we can beat state-of-the-art on that. Then we'll get on to the interesting part, specifically what I'd like to talk to some of you about is using this system for rhythm generation. So essentially, stimulating the network with some unknown, unseen input and seeing what output we get, connecting it back together, having an online interactive system. Yeah, and there are some references which you can't see, and thank you.
You've shown the connectivity matrix that results from the learning rules, so where you see kind of the resonance is specific to, I guess, the speed of the rhythm.
Yeah, you get a connectivity that's specific to that resonance pattern. So each connectivity matrix is learned online. So each sequence starts from scratch and is learned online. So we did do some experiments where we tried to keep that over the course of all the training sequences, but essentially because it's an online learning rule, you basically forget some of the old important stuff. So the initial condition with the generic connection sort of fixed that for us and gave us better results.
Any other questions?
What happens if you point these detection algorithms at well-performed pieces of music that are generally taken to be non-metric? So
Yeah,
Claude Huffler's playing a blood-sucker piano sonata.
Yeah, it's a really interesting question. It's something that I'd like to look at as well, analysing what the GFNN output would be for a rhythmic piece of music. The answer is I don't know, and no one's looked at that yet, but I think that it could be something really interesting to look at and generate some things with the system with more free rhythm and a rhythm. Yeah.
Other questions?
Could you expand a little bit on where you got to at the end about the application?
Yeah. The plan is to introduce a symbolic element to the model. So based on some of my earlier work, which was on symbolic, so we'd have an LSTM which was predicting some symbolic data like pitches, rests, that sort of thing. Couple that with the real-time, continuous time series data, which would predict rhythmic onsets and maybe as well have pulse predictions. Then you take the two outputs of those system into some kind of audio rendering of it. We think it can be all done in real time with real-time interactivity with quite small latency because once the system's trained, it's very quick. Each activation of the network is very, very quick, like 200 times faster than real time. So, and also it's predicting the next sample, so you'll reduce the latency there as well. So yeah, that's the plan. Work with some musicians in the music department at City and produce some compositions, some performances with a real-time system. We're also going to work on training the system on different data sets to see what the different rhythm predictions are, what sort of rhythmic novelty you get out of it. And then the evaluation of that will be through some statistical analysis of the rhythm and some statistical analysis of the expressive timing, and then also some interviews and listening tests with the musicians that we'll be working on.
Okay. Are there any other questions? Could you just expand a bit on generative process that you are going to do with the system?
Yeah, so essentially the model I think lends itself well. There's been some work with LSTMs on generation already. And if we extend E to produce audio output, then it's easy to create a feedback loop within the system. So you can have it just playing by itself as an autonomous system, or at point A, you can introduce another performer, or only introduce another performer, and then you get some interactivity happening there. Other people have looked at also using either noise or a chaotic oscillator to add more novelty into the system. But then some people have also just explored using data sets that the system wasn't originally trained in. So that being sort of novel data to the network, therefore then that creates novel output. So we're going to explore a few different options and see. The other thing that we'd like to explore is polyphony. So at the moment, the rhythm onset is monophonic rhythm onset. And that will work well for some data sets, but not for others, for some instrumentation, but not for others. So yeah, we're going to explore a model for polyphony and segmentation of the original audio and stuff like that. If there's time, there is. We've got 1 year left.
Okay, so any other questions? Or? No? Okay, so that's fine. Thanks.
The University of Huddersfield, inspiring tomorrow's professionals.